All right, so let's prove property 7. And we're going to use the exact same proof technique that we used in our seminar, where we're going to actually show that this holds by just looking at one entry at a time and showing that for any row and any column, the entry on on the matrix on either side is going to be the same. So let's be specific. Let's say A is going to be m by n, and let's say B is n by r. Remember, that's the most general way you can set up the circumstances that you need in order for the product of A and B to be defined. Remember, the B has to have the same number of rows as A has columns. That's what it means. That's what you need in order to actually say that A times B is defined, with A being the factor on the left. Okay, so let's say we're to take AB and transpose it. So this is the matrix on the left-hand side of the equation. So let's take the entry from that matrix in the ith row and the jth column. Well, first things first, the outermost operation that's happening, the first thing that you're going to really see if you're looking from the outside in is that transpose. So let's just deal with that first. Remember how the transpose affects the indices of an entry? If you're looking at a particular entry that occupies row I and column J from the transpose of AB, well, that's going to be the same. That'll be the entry from AB that occupies the jth row and the ith column. That's the definition of matrix transpose. But now, what we're going to do is we're going to need to write out this entry. What is the entry from the product of A and B that occupies the jth row and the ith column? Well, this is where that summation formula is going to be useful, right? So this is the sum, not from J, the sum from K equals 1. I'll come back to where this is coming from in just a moment. It's going to be the sum from K equals 1 to N of the entry from A that occupies the jth row and the kth column, and you'll multiply that by the entry from the matrix B that occupies the kth row and the ith column. Where am I getting that from? Well, if you remember, we actually wrote it down when we first defined matrix multiplication, but then we didn't use it until now. But this is actually the way you can write down a formula without having to reference dot product. That's a formula for the entry in the product of A and B that occupies the ith row and the jth column. The only difference between this and what we have is that our I and our J here, they're actually swapped. And that's because of the transpose that we applied, we didn't have IJ down there. We were looking at the subscript of JI, right? We have the entry in the jth row and the ith column. So that's why the J and the I here are backwards. Okay, so, well, what are we supposed to end up with here? We're supposed to end up with B transpose times A transpose. So, but our transposes are gone. But we could put them back, right? We could, now that we've split these matrices up, so to speak, we could put the transposes back. I'm going to work downwards because otherwise very quickly I'm going to run out of the room. So this is the sum from K equals 1 to N of, well, this is the entry from A transpose in the kth row and the jth column multiplied by the entry from B transpose in the ith row and the kth column. So notice I swapped those indices at the cost of adding a transpose there. And then similarly here, these indices got swapped down here, but that's because I added the transpose. And this kind of looks like the matrix multiplication, but notice the summation index, K, it's the outside indices now, right? And here's what I mean by that. If you go back up and look at the definition, K was actually the inner indices. It was the inside ones. If you think of these as 4 indices, the 2 inside ones were K. But in our case, in our situation, I hit undo one too many times. This K should be here. In our case, we've got the 4 indices, and the Ks are actually the 2 outer ones in terms of those 4 indices, if you were to put them in a row. The two outside ones are K. So it's not quite looking like the definition of matrix multiplication. But that's okay, because remember, they're supposed to be swapped, right? That's what we're supposed to end up with, is B transpose times A transpose. So actually, if we go like this and say this is going to be the sum from K equals 1 to n, nothing's changing here, but I'll just change the order of the two factors. B transpose, the entry from B transpose in the ith row and the kth column, multiplied by the entry from A transpose in the kth entry and the jth column. Well, now if you look at them, now it looks like the two K's are the inner index. So, and the inner of the four indices, right? The inner two indices, if you put all four of those in a row. And so that's what you need. To be able to say that this is actually the entry from a matrix product, you need the matrix, or the matrix, the index of summation had better be occupying those two inner positions here. So that's why we can freely say that this is the ijth entry of B transpose times A transpose. And guess what that means? That means that we've said the entry from AB all transposed in the ith row and jth column is equal to the entry from B transpose A transpose in the ith row and jth column. And if that's true for any indices I and j. So that means the two matrices are equal. So we can say, therefore, this property holds. Therefore, we can say the transpose of AB is equal to B transpose times A transpose. And that's the proof.